In this video, we're going to train a neural network to classify images as either being an image of a cat or an image of a dog. In our previous examples of training a neural network, we've been able to hold all the data in memory, but in practice, often our training data set is too large to hold in memory. The data is stored on our hard drive or on our solid state drive, but it's too large to hold in memory. So what we have to do in that situation is at each iteration of stochastic gradient descent, we have to read in one batch of data from our solid state drive and then update our parameters based on that batch. And so in that way, only one batch of data has to be held in memory at a time. Our training data set could contain like 1,000,000 images, but each batch might only be 32 images or maybe 16 images. So one batch of data is much, much smaller than the entire training data set. So we can hold a batch of data in memory, even though we can't hold the entire training data set in memory. So here's the data we're going to work with in this example. This directory contains our training data. This directory contains our validation data set. And this directory contains our test data set. Let's look at the training data. We have one directory that contains a bunch of images of cats and another directory that contains a bunch of images of dogs. And in the cats directory, we have 1,000 images of cats. And in the dogs directory, we have 1,000 images of dogs. And that's our training data. In the validation data set, again, we have a directory for cat data and a directory for dog data. And in the validation data set, we have 500 cat images, and we also have 500 dog images. And finally, in the test data set, we again have 500 cat images and 500 dog images. This data set is actually a small data set by the standards of deep learning. We actually could hold this entire data set in memory, but we're going to illustrate the process of how you would read in data one batch at a time. And actually, when we're doing computer vision in practice, we often don't have the luxury of having a training data set that contains 1,000,000 images. Maybe we only have a few thousand images, or maybe even only a few hundred images. Deep learning can still be effective in those situations, and we're going to discuss two important techniques for dealing with the fact that we might not have as much training data as we would like. One technique we'll discuss is data augmentation, and another technique, which is very important, is called transfer learning. Data augmentation is where you enlarge your training data set by creating new images based on the original training images. For example, you might take one of your original images and rotate it by a certain amount, or you might add some noise to it. You can apply various transformations to your original images to get an expanded training data set. And transfer learning is where you first train your neural network on a much larger data set, which is publicly available. For example, you could train a neural network on ImageNet, which has 14 million images. And then you would take that neural network, which has been trained on a huge data set, and take the convolutional layers from that neural network and freeze them and add a few new dense layers at the end of that network, and train only the parameters, only the weights in those final new dense layers using your own training data. So the base convolutional network was trained on ImageNet and then frozen, and then the final few new layers are trained using your smaller data set. That base convolutional neural network, which has been trained on ImageNet, has learned to detect many patterns which appear in images everywhere, including in your own data set. And then you only need a few more extra layers that are tailored to your particular data set. Since you're only going to be training the final few layers of this neural network, the number of weights that have to be determined is relatively small, so the fact that your training data set might be small is okay. So here's the code that we're going to use to create and train our neural network using TensorFlow. Here we have a bunch of directories where we can find the data, where we can find the training data and the validation data and the test data. This variable train data gen is an image data generator, which is a type of object provided by TensorFlow. This image data generator that we've just created knows that when we read in a batch of data, we should scale each image by this factor so that the maximum intensity value in the image is 1 rather than 255. This object train data gen is going to help us read in training data. This object test data gen is going to help us read in the validation data. Maybe it should have been named val data gen instead of test data gen. Now here, we're creating something called train generator, which is an iterator. And it's going to do the work of reading in a batch of training data for us, one batch at a time. These arguments over here provide information about what should happen when a batch of training data is read into memory. This first argument specifies where to find the data. This next argument, target size equals 150, 150, that means that each image that we read in is going to be resized to have 150 rows and 150 columns. So after that resizing, all of our training example images will have the same shape, 150 by 150. And they're color images, so they'll each have a depth of 3. This argument says we're going to use a batch size of 20. So each batch will consist of 20 images from the training data set. And this argument indicates that we'll be doing binary classification. So train generator is an iterator that will be used to iterate through the training data one batch at a time. Validation generator is an iterator that will be used to iterate through the validation data one batch at a time. Now let's take a look at the training data. Here we're setting a variable count equal to 0, and we have a for loop which is going to iterate through the training data set one batch at a time. So we're going to extract a batch of images and a corresponding batch of labels. Here we're extracting the first image from the current batch, and we're displaying that image, and then we're printing the label of that image. Here we're incrementing this count variable, and we're going to stop once count is equal to 3, which means that we have cycled through 3 batches of our data. So let's run this section of code. And we can see here we've got an image of a cat. The label is 0. 0 corresponds to cat. The reason it looks a little bit distorted is because the images have been resized to be 150 by 150. The aspect ratio might have changed during that resizing. And then here's another image of a cat. The label is 0. And here's an image of a dog. The label is 1. Next, here's the part of our code where we create our convolutional neural network. We specify the architecture. So the input is going to be a color image, 150 rows, 150 columns, a depth of 3 because it's a color image. We're going to have the first hidden layer is going to be a convolutional layer with 32 convolutional nodes, 32 convolutional filters. Then there's a max pooling layer. Then there's another convolutional layer which has 64 convolutional nodes, and then a max pooling layer, and then another convolutional layer with 128 convolutional nodes, followed by a max pooling layer, then another convolutional layer followed by a max pooling layer, and then finally we have a dense layer with 512 nodes, and the final layer of our network has one single node, and that final node uses the sigmoid activation function because we're doing binary classification. When we're doing a binary classification problem, the final layer, the output layer of our neural network should have one node that uses the sigmoid activation function. So here we're compiling our model and we're telling TensorFlow that when the model is trained, we should use the RMS prop algorithm, which is similar in spirit to stochastic gradient descent. We're going to use RMS prop with a learning rate of 10 to the minus 4th. The loss function we're going to use is the binary cross entropy loss function. That's what we use when we're doing binary classification. And the metric we're going to keep track of during training is classification accuracy. And here's the part where we actually train our model. Notice that the method we're using here to train the model we're not just doing model.fit, we're doing model.fitGenerator. This is what we do in the situation where we're going to be reading in data from the hard drive. We're going to be reading in one batch of data at a time from the hard drive. In that situation, we use this fit generator method. This first argument is the iterator that's going to be used to iterate through the training data one batch at a time. Here, we're telling the fit generator method that each epoch will consist of 100 steps of stochastic gradient descent. In other words, we're going to have to look at 100 batches of data before we complete one full sweep through the training data set. And we're going to train for 30 epochs. Throughout training, we're going to monitor our progress on the validation data set. And here we're providing an iterator that will iterate through the validation data set one batch at a time. Here we're stating that we have to look at 50 batches of validation data before we've completed one full sweep through the validation data set. That makes sense because the validation data set only has 1,000 images. The validation data set has 500 cat images and 500 dog images, and each batch consists of 20 images. So once we've looked at 50 batches of 20 images, that is 1,000 images. So that's one full sweep through the validation data set. On the other hand, the training data set has 2,000 images. It has 1,000 cat images and 1,000 dog images. So we're going to have to look at 100 batches of 20 images before we've completed one full sweep through the training data set. So now let's go ahead and run this section of code to train our model. This part is going to be pretty slow because I'm running this on my CPU. If we were running this on a GPU, it would be much faster. So now we've finished training. Let's look at a plot of the training accuracy at each epoch and also a plot of the validation accuracy at each epoch. So training accuracy means our classification accuracy computed looking at the training data. Validation accuracy means our classification accuracy computed using the validation data set. And here we can see that the training accuracy continues to improve, approaching 1, whereas the validation accuracy levels off at about around 70% classification accuracy. Let's also look at a plot of the training loss at each epoch and the validation loss at each epoch. Training loss is our cost function evaluated using the training data. Validation loss is the value of our cost function computed using the validation data. And we can see here that the training loss continues to decrease, getting closer and closer to 0, whereas the validation loss begins to actually increase after maybe 10 or 15 epochs. So we see that we are overfitting here. After 10 or 15 epochs, we have begun overfitting. We've discussed several different ways to guard against overfitting, such as reducing the size of the model or using regularization. And next, we're going to discuss a new idea, which is to use augmented data. We're going to augment our training data set. So we're ready to use data augmentation. That means we're going to enlarge the size of our training data set by applying random transformations to the training data. By applying random transformations of various types to the images in the training data set, we can artificially create a much larger training data set. And Keras makes it easy to do data augmentation. And the way we do it is we're going to redefine our image data generator for the training data. Remember earlier, we had created this object called train data gen. This was an object of type image data generator. That's a class provided by TensorFlow. This object helps us with reading in the training data one batch at a time. When we created our image data generator for the training data set earlier, the only instructions we gave it then were that whenever we read in a batch of data, each image in that batch should be rescaled by this factor. But now to do data augmentation, we're going to redefine this train data gen object. Here we have our new definition of this image data generator for the training data set. All of these additional arguments here are describing how we want data augmentation to be performed each time we read in a batch of training data. So what this is saying is that whenever we read in a new batch of training data, each image in that batch should be modified in the following way. It should be scaled by this factor so that the maximum intensity value will be 1. It should be randomly rotated by by up to 40 degrees in either direction. So we're going to apply a random rotation to this image. And the image should be randomly shifted, either randomly shifted to the left or randomly shifted to the right. And also, each image should be randomly shifted up or randomly shifted down. And these numbers, 0.2, these control the amount of the shift, the size of the shift. So if the image that we just read in has 100 rows, let's say it's, for simplicity, let's say it's 100 by 100, then the maximum possible random shift in the horizontal direction would be 20 pixels, and the maximum possible vertical shift would be 20 pixels. That's what this 0.2 means here. It describes how large the shift is allowed to be, and it's a random shift. Also, we're going to randomly apply a shear transformation to each image. And we're going to randomly zoom in a little bit on each image. And finally, we might flip our image horizontally. So what we do is we apply a random transformation to each image in the batch, and then we proceed to perform one step of stochastic gradient descent. Our batch still has 20 images in it, but these images have been transformed. By applying these random transformations, we have effectively increased the size of our training data set by a large amount. It's in an artificial way. It's probably not as good as if we had just collected a very large amount of brand new training data. But still, even though the data has been augmented artificially, this still turns out to be a very useful thing to do. Let's take a look at the effect of these transformations. Here is a section of code that reads in one image from our training data set and applies 4 different randomly selected transformations to this image and displays the results. Let's take a look at this. Okay, here we have 4 different images, and you can see it's the same image, but it's been transformed in 4 different ways. And you can see each image has been rotated. Each image has been shifted horizontally and vertically by a certain amount. Each image has been zoomed in by a certain amount. There's been a certain amount of shear applied to each image. And you can see there's a horizontal flip. If you compare these 2 images, there's been a horizontal flip between these 2 images. So these are the kinds of transformed images that we're working with here. So now that we have redefined our image data generator in order to do data augmentation, we also need to redefine this iterator train generator, and then we're ready to just retrain our model. And this time, and that's all we have to do. This time when we retrain our model, we will use augmented data. This time we're going to train for 100 epochs. I'm going to change this quantity to 100. We'll train for 100 epochs. There's one more change that I want to make before we train our model using augmented data. Here, when we define our model, I want to tell Keras that we should use dropout in the final hidden layer, which contains 512 nodes. So I'm going to add a line that says tf.keras.layers.dropout, and the amount of dropout that I want to use is 50%. Dropout is one of the regularization strategies we've learned to prevent overfitting. And this will help us prevent overfitting in this case. So we're doing 2 new things now. We're using augmented data and we're using dropout when we train our neural network. So let me redefine our model and let's recompile the model. And now we're ready to train it. So I'm just going to run this section of code. And now the training has begun. So we've finished training and now we're ready to look at the results. So let's just rerun this section of code. Okay, and now we see that we're not observing overfitting anymore. Even after 100 epochs, the validation accuracy is continuing to improve along with the training accuracy. So whereas previously, without these 2 techniques, without doing the data augmentation and the dropout, we had begun overfitting rather soon. Now, even after 100 epochs, we're still not overfitting. And let's look at the That's the accuracy. Let's look at the training loss and the validation loss. Okay, so again, we're not observing overfitting here. The validation loss is still continuing to improve. There's a general downward trend even after 100 epochs. And let's look once more at the accuracy. Here, after 100 epochs, we have what looks like about 80% accuracy, 80% validation accuracy. So that's a significant improvement. Previously, we had about 70% accuracy on the validation data set, and now we're at about 80%. So that's a good improvement.